Well, then I'll just leave the stage to Felix. And then it's a really, well, I'm Dutch. So I'm supposed to be able to pronounce this, but we don't get the dots on the O's. So Felix Greubert.
That's right, yeah.
Right?
Thank you.
Yes. Good. Give him a big round of applause.
Yeah, thanks for the introduction, and thanks for coming to my talk. So this talk is about automatic identification of crypto in software. And this work is the result of my master thesis, which I wrote in beginning of this year. I submitted it to the University of Bochum, Germany. And since then, I've been working for Google in Zurich. So these slides are also online later this day or maybe tomorrow. And also the code and everything else will be published. You can actually find the link to the code and the thesis itself in the Pentabarf system, in the Fahrplan. So you might have come across videos of movies you would like to watch, and then there's a display where it says, you need to download this codec from XYZ and to install this codec, otherwise you won't be able to watch this movie. And after you or a friend of yours installed that codec, he might come across something like this. So if you don't get access to your files anymore suddenly. Everything is encrypted by this evil malware. You won't get access to them without making of what we need, which is the saying of the malware authors, and they used the especially secure RSA 1024 algorithm to encrypt your files. So this is my main motivation for doing this kind of work. I wanted to look at malware or other kinds of software and try to find out how could I automatically find out which kind of crypto is used in that software product, and also find out what are the keys, how is it changed? Is it only RSA with AES, or is there also a hashing function, and so on and so forth. So this is actually not a malware, but it's a subtype which is called ransomware. Ransomware is malware which wants you to send them money, and if you send them money, you get a cryptographic key and maybe also a tool to decrypt your documents, your, for example, PDFs and text files. So this malware is actually called GP code. It uses AES in electronic codebook cipher mode with a 256-bit key and the strong algorithm RSA 1025. Of course, there are other examples of malware, which are listed here, which use cryptography. Shadowbot has its own implementation of MD5 and also uses XOR for obfuscation. Configure used the OpenSSL SHA-1 and also a reference implementation of the MD6 submission to the SHA-3 competition. This reference implementation of MD6, which is not yet out there, well, the implementation is out there, but it's not really a standard for SHA-3. But this reference implementation actually had a buffer overflow. And the malware authors used that reference implementation in their malware. Sadly, you couldn't really exploit it to gain command execution, but they later fixed, they were aware of this flaw in their reference implementation and later brought out a malware update to patch their configure distributions. Waldec uses a statically linked OpenSSL AES with a zero initialization vector. And they had a key exchange protocol which not only used always the same key, so you speak with your server, negotiate a key, but the server always chose the same key. There was no random choice by the server, it was always the same key, so that was, on that point, was flawed, but also the key exchange happened over an unauthenticated SSL-like channel where the well-decked client did not really check the server certificate, so you could also man in the middle it. Netroot actually had a very interesting file network of 58 rounds. And it first looked like they use a really large key, something over 64 bits or something like that. But it turned out that their key scheduling in the file network for encryption was only effectively 32-bit. So, and therefore you could brute force the 32 bits and then find out the key, or the key and the contents of the packets. And they also implemented SHA-1, but for SHA-1 you have special constants which are your initialization constants. And they are quite significant for SHA-1 and also well chosen for SHA-1. But what they did, they used SHA-1 implementation, but only changed the initialization vectors. So if you were a malware analyst and were to compute a SHA-1 over their packets, for example, you would get a different SHA-1 sum because they used different IVs, initialization vectors. Agobot used plain old IRC over SSL. Sometimes that works too. Storm had the very secure authentication of 56-bit RSA, which is not long enough. More recently, Nugash, they used also quite strong crypto, and they, for the first time, had a design which was somewhat promising. So my motivation was to look at these kinds of malware and decide how could I help an analyst to find the crypto which is used by a malware or by something different, like a DRM system or anything else which uses crypto. And my second motivation came from the system verification perspective. If you go back, and it's always good to cite someone very past in a master thesis, so I went back to the 18th century and cited Kerckhoffs, who back then proposed that a crypto system should be secure even if everything about the system except the key is public knowledge, which is widely accepted by cryptographers today, public cryptographers of course, that the design of the crypto primitive should be public and should be analyzable, and this is all the open source thinking. Shannon later on summarizes it as the enemy knows the system, and Raymond, Eric S. Raymond in 2004 was writing about the incident with Cisco where he wasn't really trusting Cisco because he doesn't have access to their source code, and therefore he postulated that any security software design that doesn't assume the enemy possesses the source code is already untrustworthy. And I would say you can really extend that because you don't really need access to the source code, but rather you can also reverse engineer the source code. So every design which doesn't assume that you have the source code or you are able to reverse the source code is already flawed. So in the security evaluation, one has to find out whether the system is secure, whether it's a secure cryptographic design, and therefore you have to find out as an analyst what kind of crypto is used, where is it used, when is it triggered, where is it located in memory, and so on. And this is, of course, difficult if the source code or design plans and code is not public, which is the case in like the malware and examples I gave before, and also the case with digital rights management systems or any other binary you have. So my proposed solution is to do a two-phase approach. First, you run your target binary, generate a trace file which contains instructions and memory, and then later on analyze this trace file and generate a report what kind of crypto has been used. In the thesis, I wrote down this thesis that if if a standardized cryptographic primitive with its input and output is present in an execution trace, an algorithm exists to identify and verify the instance of the primitive, including its parameters, which is kind of important because you do not only want to know whether it's IES or DES which is used, but also you want to know the parameters which are used. For example, the plain text, the ciphertext, the key, because you really are interested in the payload the malware is sending, for example. And I also, of course, did some constraints, some assumptions for the thesis, because I didn't want the work to spread out too far. So I assumed that for the thesis, I assumed that the code is not self-modifying or obfuscated. I did some tests with one-stage packers, and I'm going to talk about this later, but I did this assumption to have a baseline to build upon. Also, I did not take a look at interpreted code or just-in-time compiled code, and I'm only limiting this to cryptographic primitives, not general functionality of software, which would be insane. I also do not detect the mode of operation, whether it's electronic codebook or CBC mode, or and I also don't take a look at compression or padding. So I defined some kind of moving targets for Windows 32 and x86, which are these here, you see over here. These are moving targets because you have an original definition of the cryptographic primitive in the original paper, but then you have errata, which is later on compiled and written by the scientific community, and they say you shouldn't use that key, or you should watch out for this implementation-specific attacks. Then you have optimization on the source code level, which gets us to the final implementation, which is then again optimized depending on compiler and compiler options to the final x86 compiled code. So I took 4 different libraries, open source libraries of cryptographic code: bcrypt, cryptopp, Gladman's AES implementation, and OpenSSL. I linked them differently, used different compiler on Windows, and used them in different mode of operations. And then I did my related work research for this topic, and started with the most common way one would start is to look at reverse engineering forums and see what are the bad guys using, what are reversers using, what is already out there. So here you see on the table in the top left 6 different reversing tools to find cryptography in static binaries. That means that you first have to unpack your packed malware, for example, and then run this tool on the binary. They are for different platforms. One crypto analyzer, this comes with PEID, which is a tool to fingerprint packers. The FineCrypt plugin is by the IDA Pro authors, and one plugin for OllyDBG. Furthermore, there are 3 standalone tools. In the table below, you see their performance. Plus means that the algorithm was found by the tool. Minus means it was not found. And the number next to it means the number of false positives. Of course, none of the tools detect dynamically linked or dynamically generated code, which is, of course, an advantage I have to mention when I'm using dynamic instrumentation to look at my code, which is an advantage these static tools don't have. They are mostly working using byte-oriented signatures and look for constants in memory or in the unpacked binary. The evaluation shows that all detect MD5 because MD5 is quite significant to its constants. None of the tools detects RSA, and RC4 is only detected once. Because RC4 has a very algorithmic approach and doesn't have really lookup tables or constants which could be used to fingerprint it. In the research community, there are 3 significant papers. One is by Wang and co-authors. They did a proof of concept with Egobot, which I mentioned earlier, which uses IRC over SSL. What they do is they look at tainted data and follow it through the application executions. All these 3 approaches are using dynamic instrumentation or some other sort of dynamically introspecting into the malware. And one, they watch the execution code flow and specifically look for bitwise instructions. For example, XOR and rotate left. And then they compute a cumulative bitwise instruction percentage, which first goes up, and at the turning point between the decryption and the encryption phase and the finally decrypted phase, at the turning point, the cumulative bitwise instruction percentage goes down, because in cryptographic routines often have a high percentage of bitwise instructions. Therefore, after the ciphertext has been decrypted, the amount of bitwise instruction decreases. Caballero, they took their finding and said, okay, what happens if you have multiple encryptions and decryptions in your program? Then this cumulative percentage doesn't work so well, because you have it going up and down and cannot really figure out which are the turning points where you can, at the turning point where you can actually do a memory dump and then get your plaintext which you want. So they said we only look at encrypted block processing, and they used a blockwise or function-wise bitwise instruction percentage, and didn't really count up the percentage of bitwise instructions. Noel Lutz, he took a completely different approach. He also used tainting of data, which comes in over the network, and followed that data to find loops over that data. And then he looked, how does this loop manipulate the data? Is there a decrease or increase of information entropy after the data has been decrypted? If so, he said that if that's the case, there has been a decrypted packet. Because if you look at ciphertext, it differs vastly in information entropy from a plaintext. So, and he also used loop detection to find these loops, and then also used Walgrind's tainting to follow the data through the loops. Further approaches were quite early in the 90s by Shamir and Janssen. They wanted to find RSA private keys in software, because back then often software still had private keys embedded into the memory, for example. And they found a method to exploit the characteristics of the RSA system, which has the NPQ characteristic, and then we're able to find these large numbers in memory, and we're able to find the private key for an RSA encryption system. More recently, Halderman wrote a paper called Code Boot Attacks, which was also quite well covered in the press, where they used these laptops. For example, you have a stolen laptop, want to get the hardware encryption, the disk encryption key, then opened up the tray where you can get access to the memory of the laptop, froze the memory, and then took it out. But then you have to dig through 4 gigabytes of memory to find the key, right? You have the memory of the computer you want to analyze, but have to find the AES key for the hard disk encryption in memory. So what they did is they exploited the characteristic of AES round keys. AES round keys often have, they are pre-computed in memory often. So you have a 128 block sitting next to a 128 block, and then you can compute the next round for this block and compare them, and then thereby find the AES key in memory. Stevens and Baldwin, they tried to find shellcode in PDFs by looking at certain strings in the PDF and trying to find XOR pads, which later on are XORed up to a shellcode lying in that document. So as I said before, our approach is to first do a dynamic binary instrumentation and then later on do the analysis. First, I will talk about the dynamic binary instrumentation. We used PIN for the as a baseline tool for the dynamic instrumentation, and wrote a PIN tool to instrument the target binary using PIN. PIN is a free of charge tool provided by Intel, and you can use it, for example, for performance tests and but also to monitor self-modifying code. The PIN tool we wrote can be filtered by a DLL name or thread ID. You can start after a specific number of instructions in order to skip an unpacker, for example. It records a compressed trace where the debug information is compressed in the form that you don't have to, for each instruction, you don't have the actual function address, function name or DLL name. And of course, the dynamic approach has the constraint that the code must be executed. If the malware doesn't start executing the crypto routines which we want to monitor, there is no chance for getting there and being able to monitor it. And an advantage of the dynamic instrumentation is, of course, that you are able to monitor, for example, indirect branches, or are able to monitor what kind of data is actually worked upon. The trace file looks like this. We have a line, for example, for memory access, where you can see a read of 32 bits at a specific address and the value actually read. And you have lines for instruction addresses with a compressed library name, compressed function name, an offset to the function, thread ID, and a disassembly and change registered. So if you collect the trace file, you can later on put this trace file into the analysis phase. I did take this approach of the two-phase because I wanted to have the tracing framework interchangeable. So I would be later on able to exchange the PIN framework for another framework like Wallgrind or Bitblaze, because the framework is highly dependent on performance, and also sometimes you cannot really trace a malware under this framework, so you have to take a different framework, and the trace file acts as an independent layer here. If we go to the analysis phase, I first parse the trace file, filter again by, for example, thread or function name or DLL, and then queue the instructions up to later analyze them. With the queue, you can also work with an interactive console based on IPython, and you can, for example, do some debugging tests there. And you can also export the structure. With structure, I mean, for example, basic blocks or control flow graph, and export it to PDF, which looks like this. On the right, you see a control flow graph of the XOR testing application, which was exported using GraphViz. To generate the executed basic blocks, I do a 2-pass over the sequential instructions. First, I determine jump points, where is it jumped into and where is it jumped out, and then during the second pass, I do the population of the data structure. The control flow graph is then just compiled from the sequentially executed basic blocks, and the advantage, again, of dynamic instrumentation here is that you not only get the indirect branches, but also are able to see how much is the edge being taken. For example, you see here, this edge is taken 252 times, and this is taken 2 times, for example. And based on that, I can do a loop detection, which I adopted from Tubera's algorithm. This loop detection algorithm works by detecting multiple executions of the same address and exposed several features. There is also the Langer-Otarian algorithm, but this one doesn't show you how many times is a loop actually executed, how many iterations does it have, and how are the loops nested, which is quite interesting from the analysis perspective. So here's an example of the loop detection algorithm. On the top left, you see the target code, which should be detected. And the loop detection works by using a loop stack. Again, if an instruction has been executed multiple times, the iteration is incremented on the loop stack, which you see right here. Here's the first assignment to C, and here's the second. So C will be, because this is an address we already seen before, without branching out of the yellow part of the loop. The loop stack is incremented here, because there we enter an additional basic block in the red one. We add another layer on the loop stack, which is the red layer. Also for, not only for branches, but also for calls and returns, the loop stack is incremented with another layer and again counted. So the result of this example is that the outer yellow loop is executed 2 times, and the inner red loops are iterated once and twice, and then again each call the blue basic block for one iteration. Besides the loop detection and basic block generation, we also want to detect values in memory. To do that, we use a memory reconstruction algorithm, which is needed because you have usually cryptographic values are larger than the register size in modern CPUs. So you have to find out where are the keys located. So for the trace, we walk down the trace and then do a recursive search to check whether at the next address lying in memory, whether there's another access to that memory address. For example, if we check the address 0 and then we are at the address 0 at this axis of memory, we check whether at the next address, namely last address plus length, whether there's another access to memory, this one here. And then we compile this to the next block. For example, for a candidate for a key. We continue our search for each of the next addresses, but also split it up if there are multiple references to memory. For example, here you have multiple accesses at this address there's an access to this value, but also to this value. So we associate these two values because they are both, for example, a read of the same length and are also referenced in the same address space. So, for example, this blue here, this blue one, this is referenced from an address which is not nearby the address of this one or these two here. So it doesn't get associated with these values in memory. The last phase of our analysis is to find the actual crypto based upon our restructuring of the code. And to do this, we exploit several identification observations with cryptographic code. As I mentioned earlier, cryptographic code makes excessive use of bitwise arithmetic instructions. On the right, you see an example from the OpenSSL DES, which uses, if you see in the middle, if you look in the middle, you see a lot of instructions which are bitwise. And you can exploit that characteristic as shown by Caballero and Wang to find cryptographic code. And for example, Caballero also found out if you compare the bitwise arithmetic instruction set with BMP, another identification we made is that the constant and sequences of mnemonics indicate the type of cryptographic algorithm. You see on the bottom here different instructions, different implementations of MD5, but they all start with a rotate left 7. And their next instructions are also the same, so you could, to find an MD5 implementation, you could use the chain of instructions rotate left, add, move, XOR, which is all the same for all three implementations. Further observations we made is that, like Noé Lutz noted, cryptographic code contains loops. However, often in implementations, loop unrolling is used to make the code more effective, to optimize it. But so you cannot really say if there's a loop of 16 rounds, it must be in DES implementation, because DES uses 16 rounds, but you cannot really tell from that, but you can use it as a further indicator to pinpoint the cryptographic code. And the last identification we made is also the most significant identification method, is that input-output relation to the cryptographic code most often has a predefined verifiable relation. So you have something which you put into your AES, but the output for the same key and same input is always the same. So you can exploit this relation, which is predefined. And if you know the algorithm, you can use the reference implementation to actually verify this instance of an AES encryption in code. There are some cryptographic primitives which don't have this deterministic relation, but we don't look at these for now. So I implemented several identification methods. A most naive identification method using signatures on debug symbols of common APIs. Then I used several constants, which were also used by the reverse engineering tools, and tried to find the constants in memory. I implemented a method to find the sequence of mnemonics, like in the MD5 example, to find the reoccurring sequence of a certain computation. I'm going to talk about the mnemonic constant tuple identification method later. I implemented the related work methods and also more generic identification methods I'm going to talk about now. The method, the mnemonic constant method, for each implementation, defines a set of bitwise instructions which have also a static constant. For example, rotate left 14 hex. And then for each algorithm, a unique set is built. For example, here, the dotted intersection MD5 set, which is composed of the OpenSSL, of the intersection of the OpenSSL MD5 and bcrypt MD5 and cryptopp MD5. So this is one set which can be used to identify MD5, but there's a further set which is the unique MD5 set, which is the subtraction of other implementations. For example, if you subtract the OpenSSL RC4 implementation out of the intersection set, you get the unique set. The unique set has, of course, a stronger relation to the algorithm, but is also smaller. If you use that to identify the type of algorithm, you get this table. In order to further visualize this table, I used a tool to associate the x-axis and y-axis of the table around a circle. And here you see the which algorithm found, which signature found which algorithm. So here you see the bcrypt AES signature, and this signature matches only the bcrypt AES code with a cell value over 70. The MD5 cryptopp signature finds MD5, cryptopp MD5, but also with a smaller value, some false positives. The unique signatures work better, of course, but they also have, for example, for AES, no unique set. There are 0 false positives for the RSA unique signature and 0 false positives for the DES and MD5 signature, which each map to the cryptopp MD5, bcrypt MD5, and OpenSSL MD5 signatures. RC4, as I said before, has a very algorithmic implement structure, and therefore it doesn't have a very large set of unique tuples. So there are a much higher number of false positives for the RC4 unique signature. One generic method I implemented was the loop differ. You can think of a loop as this three-dimensional cube where each axis has a number of executions, instructions, and iterations. So, for example, here in the green axis, you have the instructions. Down there, executions and iterations. And for each point in the cube, you can compare this block to the next iteration or this block to the next execution of the loop. And I tested the relation between these values, for example, for XOR relations and for counter, whether there's counter incrementing between these iterations or executions. The best generic method we found was the data verifier method. There we used first filtered for candidates for ciphertext and keys. For example, we filtered out certain length of memory values we found in memory, and also sliced those values in order to fit nicely for a candidate for a key here. Then for example, we said that there might be some AES code in that part of the trace, and then we try to find candidate values for the key in plaintext, give these values to a AES reference implementation, get a ciphertext out, and if we actually find the ciphertext which we get from our reference implementation, if you find it in the trace file, for example, here's 128 write. If this is equals, we actually detect an AES not only with the key, but also with the plaintext and ciphertext, and verified its relation. The general performance of the tool is okay for a prototype. The trace files are between 10 and 90 megabytes, and the tracing times and analysis times are between several minutes and several hours. Our real-world experiments we did were that we packed an XOR application, which does a simple XOR, packed it with SPAC, a common packer, and this increased, of course, the trace file by a factor of 17. However, after it has been unpacked, the analysis routines were still able to find the core loops of the XOR encryption and were able to find the XOR key and XOR plaintext. We also tested the curl command line tool to initiate a HTTPS session with a pre-configured AES-256. And OpenSSL, of course, curl uses OpenSSL. And this trace took 7 minutes and 45 megabytes, and the analysis found the plaintext, key, and ciphertext of 94% of all SSL blocks. Coming back to the malware now, the GP code malware was also run through our prototype implementation. And what you see here is the AES key, which was used to encrypt the files, encrypted with the public key of the malware author. And while running it through our analysis tool, we found that for each file, it does not completely encrypt it, but rather only encrypts the first blocks. So this is the original file. And down here, you see the modified file by GP code. And it only encrypts these blocks here. And it uses ECB mode and also a static key for every file. Also appends a signature down here. And while running it through our analysis tool, we found using our reference implementation method, we found this instant which was used for this file right here. And here you can see the encrypted ciphertext EA0B, which was later on used to corrupt the file. So further work I want to do in that area is to implement this relation checker with the reference implementation and a dedicated PIN tool, and do maybe a proof of concept with Skype or something else. Also, PIN does not really work quite well for malware, so there might be a good option to switch from PIN to another tracing tool or tracing format like BitBlaze provides. Also, there's some open work to be done in the right now more naive signatures. They could be done better using machine learning methods. And my vision for this project is to have a tool to actually run a binary through this tool and later on get the complete definition of a cryptographic protocol. It would be nice to have a tool to trace a file, but then not only get in each instance of all these cryptographic primitives, but also be able to chain these cryptographic primitives together and get a definition of cryptographic protocol from the binary. The source code is available here. So to summarize, if you use a static key, you failed before, but now you fail more faster. Because in my opinion, like I showed, the automatic identification of cryptocode is feasible and gets better. The applications of the proposed methods include malware, DRM systems, closed source, obfuscated software, and my guess is that it will find interesting results. Further work, of course, has to be done with machine learning, and further work, of course, in the dynamic binary instrumentation systems. So thanks for your attention, and I'm open to questions now.
Wow. Wow, wow. Okay, I am flabbergasted. Anybody, do you have questions? Would you please come up front? Just come and stand next to me and we can have fun asking questions. Yeah.
One question, one remark. Has no one ever tried elliptic curve crypto? Because it's more complicated in structure.
That's very true that it's more complicated and would be more complicated to detect, but I'm not aware of any attempts to detect it.
And then one remark or one thesis, I would say that any protected implementation against side channels is not vulnerable to any of these attacks, because then you have these randomized execution paths.
Well, that's very true, for example, for blinded RSA, but it also depends on what's your kind of introspection you have for the smart card system. So for a smart card, it may be true, but if you have an x86 code which is running on your normal computer, you can normally inspect that code by tracing it. And if you're able to trace the code, you should be able to detect it.
S-boxes, for example, in AES.
That's right. Yeah, that's true. Yeah. Mm.
Okay, could dumb people like me use this?
I hope so. I hope so.
Do you fear your work could be abused for enforcing import or export restrictions?
Can you say that again?
Do you fear your work could be abused to detect an export attempt or an import attempt on forbidden software, cryptographic software?
Sorry, can you please again repeat the question?
Guys in the back who are leaving, could you please do it more like quietly so we can understand what they are talking about? It's already hard for me to understand, so if you be quiet, thank you.
Could this program be used or abused for detecting automatically software that is transferred from a state that, from a country that prohibits export of such software?
Yeah, that's true. Although I am not aware whether it's still enforced for the US. I think you're referring to the US here? I'm not sure whether it's still enforced in France or the US. So, but I'm sure that could be used for that purpose.
Hi. I would like to know if I want to use crypto on an embedded system and I can't or don't want to protect the key by some hardware measure, what would be, in your opinion, the best way to protect this key or crypto algo?
In an embedded system?
Yeah.
Well, I cannot really answer this question because I'm not very into reversing embedded systems. But from a
or in general in any computer microprocessor environment.
So one thing which was also already mentioned is that you could use some randomness to the algorithm. You also, of course, with an embedded system, you might also take care that the memory is not written to main memory, but maybe stays in a cache, CPU cache, somewhere where the cold boot attacks, which were described by Hallerman, wouldn't be applicable. So that would be another option. Otherwise, I would recommend to design a secure system and not use snake oil crypto, but rather use a secure design for whatever you want to do.
Okay, thank you. I want to roll out some embedded system where it's from a design standpoint not reasonable to have some hardware measure to protect the key I use.
Sure. Yeah. Sure.
Okay, come back to you afterwards. Okay, thank you.
I guess there are much more questions, aren't there? No questions at all? Really, I don't believe you. So you are telling me you understood every word he said and you have no questions at all? There was no, I heard some yeses, but not all yeses. So that means we have really a lot of questions to handle. No, seriously, no questions? No? Wow, you smart people. I feel really dumber by the minute. And next to you, I feel even stupid. It's ridiculous. Well, I want to thank Felix so much for your presentation.
Thank you.
And I guess